Welcome back to the machine learning lecture. You've made it to the final week this semester where we will learn about certain advanced machine learning topics. We will think about certain aspects of machine learning which turn out to be very important when you deploy machine learning systems in the real world. Specifically, we're thinking about what happens when you deploy machine learning systems in real applications. And while there are many different aspects here that we have to consider, in the interest of time, we'll focus on two very important aspects, and those are privacy and fairness. But before we go there, let's back up a little bit and consider what we've been talking about throughout the semester. In most of our discussions here, we were focusing on optimizing some sort of simple metric. Usually, that was framed as minimizing some sort of error. If you think back to the linear classification lecture or the lecture on support vector machines, the goal there was to find a classifier which predicts well on unseen data, or in other words, a classifier which has low misclassification rate. In the lecture on regression, we wanted to find a linear regression, for example, a linear fit, a linear function, which has low sum of squared errors. In the lecture on dimensionality reduction, we talked about finding a low dimensional representation which leads to low reconstruction error. So in almost all of the cases that we were discussing this semester, we were focusing on minimizing some sort of error. Sometimes we also talked about efficiency, so what is the computational complexity of a certain algorithm, and what are the trade-offs of using a maybe more expensive algorithm versus a cheaper algorithm, and so on. But mostly what we've been talking about is accuracy and, yes, sometimes efficiency. Turns out that when you take these techniques that we've learned and apply them in real-world applications, you have to think about much more than this. And as machine learning systems become more and more widespread, as they become part of other technical systems that you use every day, essentially, we have to think more broadly and in general about the societal impacts of some of these methods. And this is particularly important when machine learning systems are being used in safety-critical applications. For example, you can think of maybe some sort of system used to control a nuclear power plant, where of course you have to really be careful about what the system does and what kind of errors it makes. Or what is more applicable is when machine learning systems are used to make decisions that involve humans. So for example, when machine learning systems are used to decide who gets a loan, who gets invited to a job interview, whether you qualify for parole or not, whether you qualify for adopting a kid, and so on. And this is really not only abstract, and it's really that machine learning systems are being used to help make some sort of some of these decisions. So we have to think about what are the downstream applications. And what is here especially critical is when machine learning systems create additional feedback loops. So think about a recommender system. We've talked about this in some of the previous weeks. And as the recommender system is, for example, recommending which movies you should watch, or which YouTube videos you should watch, or which songs you should listen to, of course, this has an effect on your future behavior, which will then get picked up by the machine learning algorithm, which gets then retrained on future data, and so on. And often it's very difficult to predict what kind of feedback loop this is going to create and what will be the end state. In general, we should always be asking ourselves whether we are optimizing for the right thing. Let's look at a news recommendation system, for example, where we could be optimizing for engagement, which means that we try to recommend articles which are most likely going to get attention, which means that most people are going to click on them and stay longer on our platform and interact longer with our system. But this could have some unintended consequences that we end up promoting, for example, fake news, because those articles have more outrageous claims or are more inflammatory, which means more people are likely to click on them. And it's not clear whether it's the right thing to do that our platform ends up promoting more fake news, because what we were optimizing for was engagement. In general, it's really difficult to figure out what is the right thing to optimize for, and we might even have competing objectives, and it often is not clear how to balance these objectives. But we should be thinking about them instead of just training some sort of system, putting it in the wild and saying that we're done. In practice, we have to consider many other different aspects beyond accuracy or in addition to accuracy. For example, if we're working with sensitive information, such as medical data, we have to make sure that our model doesn't reveal or leak any of the sensitive information about the individuals in our training data. And this can happen. Often our models are so powerful that they can actually even memorize some of the data in the training set. And then, just by looking at the final trained model, you can actually figure out or reconstruct sensitive information about the individuals in the training set. And of course, this would violate their privacy, and we would like to avoid it. Even if it's not medical data, maybe you were working with a recommender system, we would like to avoid that, for example, you can reconstruct the rating history of a particular user, because this would, of course, violate their privacy and so on. In addition to privacy, often we care about security. For example, maybe you're training a classifier that tries to predict whether your system, whether an email is spam or not, or you're trying to build a classifier which predicts whether a user is a real user or a bot. In this case, what we would like to avoid is that a motivated adversary can manipulate the classifier in order to avoid detection. So you can think of, again, to the example of spam detection. The adversary, of course, wants to get their spam email to not be detected. So they will modify the text of the email. They will add certain changes to the input in order for the classifier to be fooled. And turns out that many of the classifiers that we train are vulnerable to these kinds of adversarial manipulation. We'll briefly talk about this in some of the next slides. We would also like to try to avoid that somebody poisons the training data, so changes the instances in the training set in order to make the classifier have a certain behavior, or to steal the model parameters, and so on. A different aspect is fairness, where we have to think about how our classifier or how our machine learning system affects different subgroups of people. For example, you can have a classifier which has 99.9% accuracy, which on a first look seems excellent, right? It's almost 100%. But what this classifier could be predicting 100% correctly for a particular group of people and 0% correctly for a different group of people. And of course, we would like to avoid that, and we would like to treat all groups equally, more or less. And we'll talk about, again, fairness in many more details in the remaining of this lecture. Something that's very related and also potentially going to become even more important in the future is explainability. So whenever you're using a classifier to make decisions about humans, you would like to kind of give the reasons why the classifier made the prediction. So if, let's say, the classifier decides whether you get a loan or not, it's not going to be enough that you say yes or no, or the classifier says yes or no, but you need to kind of justify what are the reasons that the classifier said yes. And if this is, let's say, a simple linear classifier where it's you just have some weights for each of the features, it could be easy to figure out, because you can see that this particular feature was high times the weight, which is high, and that's why the classifier said yes. But when the models become much more complicated, like deep neural networks, it might be difficult to really say which features contributed the most to the current decision. And of course, there are techniques to distill the decisions made by models. Sometimes there might be even some legal requirements that you have to consider. For example, there are some requirements from GDPR which are closely related to this notion of explainability that we mentioned here. But, for example, from GDPR, there's also requirements that every user has the right to ask that all of the data associated with them is deleted from your system. And if the data is simply stored in a database, you can easily do this. But if you've used user data to train a machine learning system, some of their information is implicitly encoded into the model parameters. And then it's not clear what it means to remove this information about this user from the model. Of course, what you can always do is you can retrain the model from scratch, removing that user from the training set. But if you have thousands of requests to remove data a day, retraining every time from scratch might be infeasible. There might be some other requirements related to copyright or intellectual property. We talked about in the previous lectures about generative models, such as the Gaussian mixture model, where you can take a data set of images and then learn a generative model which learns to generate new images, or a data set of songs and you train a generative model that learns to generate new songs. And then the question is, if this starting data set has images which have copyright, are the newly generated images also copyrighted or not? And who does the copyright belong to? And so on. Actually, in many of these cases, there is no legal precedent yet, and it's not pretty clear yet what is the regulation around different types of machine learning models. A different notion here which is important is accountability, which means that we should be able to verify somehow or audit machine learning models, usually from an external place, to verify that they function as intended, and so on. In addition to these specific issues, such as privacy, fairness, or robustness, we should also be thinking about the long-term and broad impacts of the machine learning and AI systems that we're building, including all of the ethical questions that surround them. Take, for example, self-driving cars. Maybe we're in a situation in which an accident cannot be avoided and the car has to automatically decide between preferring the safety of the passengers inside versus the safety of the pedestrians outside the car. It's really not clear how to make this decision. What if we have one passenger versus two pedestrians? 1 versus 10 pedestrians? What if the pedestrians are children? And so on. Here we immediately run into very difficult ethical dilemmas called trolley problems, which even though ethicists have been thinking about for centuries, we still don't have a good solution for. But if you want to build a self-driving car, at some point you have to write some code which decides between these alternatives. In different scenarios, we should be thinking about whether building a machine learning system, building some classifier, some model, is a good idea to begin with. Just because we can do something doesn't mean we should. Some examples here include autonomous weapons or facial recognition software, which then leads to surveillance and so on. What happens if social network platforms or social media platforms are optimizing only for click-through or for engagement using machine learning systems and so on? What are the long-term impacts of creating super intelligent AIs which we cannot understand or interpret? What are the feedback loops that are created and reinforced, and so on? All of these questions are very difficult, but that doesn't mean that we should not be thinking about them, even though we cannot really solve them. And maybe just as one anecdote, recently the top machine learning research conference, NeurIPS, added that every paper which is submitted to the conference has to have a special section focusing on the broader impacts of the model or the algorithm or the optimization procedure that you're proposing. And this will help us essentially think through what are the potential implications, what are the positive or negative impacts of the models that we're working on or using. You might be thinking that some of these concepts sound vague. What does it mean for a classifier to be fair? What counts as an explanation of a decision, and so on? And you are right. Even properly formalizing or mathematically writing down some of these concepts is half the challenge. This is a very active area of research, and new definitions and new formalisms are being developed every year. That being said, machine learning systems don't exist in vacuum, and there is no technical solutions to all of these issues, or only technical solutions. You cannot come up with an SVM++, which will always be fair, and so on. Because machine learning systems are deployed in society, we also have to look at social, legal, political aspects, which means that we need an interdisciplinary effort. Of course, because we know the technological part of the equations, that's what we can focus on. But we should be aware that usually to approach these issues, we need input from other disciplines as well. In the remaining of the lecture, we'll look at two technical concepts, which are differential privacy and algorithmic fairness, which try to solve at least part of the issue with privacy and fairness respectively. Usually, in applications in which we care about privacy the most, we're working with data about individuals. So one idea you might have here to protect the privacy of the individuals would be to simply remove all personally identifying information, such as names, addresses, and so on. Unfortunately, this kind of approach doesn't work in practice, and proper anonymization is really difficult. There are many examples of this, and one such example is when the US government released a dataset of medical visits for research purposes. So in order to anonymize the data, they removed all the names, addresses, and social security numbers from the dataset. But in addition to the other data that they left in, they left information about the zip code, the date of birth, and the gender of each of the individuals. And turns out that in this dataset, 87% of the individuals can be uniquely identified using this triplet. Meaning, if I know these three pieces of information, the zip code, the date of birth, and the gender, I can uniquely identify 80% of those individuals in that dataset. And of course, this poses a risk for the privacy of those individuals. In general, whenever we have a dataset with user information, the more features we have, the more there are different unique combinations which can uniquely identify each of our users. A different example is with the Netflix challenge, which we've already discussed in one of the previous lectures. So if you remember, Netflix released a dataset of 100 million movie ratings, and the goal was to build a recommendation system which is better than their internal recommendation system. And they did the correct thing, and they removed any of the user data and only released anonymized user IDs. Turns out that 99% of the users who have rated at least 6 movies could be identified by comparing their ratings to reviews on IMDb, so on the Internet Movie Database. This is essentially some different data, and by looking at the ratings, which were anonymized, and this additional data set, researchers could figure out which user corresponds to which set of ratings. And of course, this is not ideal because Netflix was hoping that the data was anonymized, but turns out they can even recover their actual real names in many cases. And these two are not the only examples. There's actually thousands and thousands of different examples where data, which is supposedly anonymously released in the public, was actually later de-identified, and the real users, sometimes even the real faces of the users, could be identified by either adversaries or by researchers. So maybe here let me give you one example to show you exactly why this is hard and why it's not sufficient to remove unique identification of individuals. Now imagine that we have this data set, and in this case we've removed any of the name, and we're only keeping the age, the gender, the zip code, whether the person is a smoker, and the diagnosis of a certain disease. And let's say all of these attributes, all of these features are important for some sort of medical research that we're doing. Maybe the zip code is not important, but let's not focus on that. Now, if we know that our user, Rebecca, is within this data set, and we know that she's 50 years old, we have already narrowed it down to 2 potential diseases that she might have. So we know that she's female, so that means all of these are potentially Rebecca. And we also know that she's 55, which means only these 2 are left. So now we know that Rebecca has either HIV or ulcerative colitis. Now, this becomes more and more the case, the more and more features we have, because again, it becomes pretty easy to uniquely identify a certain user just by the fact that they are part of a certain data set. There's other potential there's other potential problems which are more specific to machine learning models, where let's say you train a machine learning model on some data set. The data set is completely private, it's completely proprietary, you don't release the data anywhere, but you only release the model. So let's say you've trained a linear regression model, and then you release the weights of the linear regression model to the public. Well, it turns out that there are so-called model inversion attacks, which can recover the actual training data from the trained model. And this is one example of how this happens, where here we see the original phase, which was in the training data, which has not been released. And then we see that we can recover, even if we take a phase that has been blocked out, we can recover the actual original phase that has been used just by looking at the model weights, just by reverse engineering essentially what kind of training data has gone into training this model. Maybe you're familiar with a certain feature that Gmail has recently rolled out, where you can start typing some text in your email and then click a certain button, and the text will do an auto-completion part, completing your email based on a bunch of other emails that it has observed in its data set. Well, what can happen in this case is you can start typing the name and the address of a certain user, click this autocomplete button, and the model will complete other personal information about the user, maybe their social security number and other personal information. And this can be problematic because what we wanted to do is we wanted to create an autocomplete email system which was helpful for our users, but we ended up revealing private information. And this happens in general, where language models end up, not only for email, but different natural language models trained on sensitive information end up memorizing and then repeating that information when prompted at inference time. So the question that we're going to try and answer in the remaining of these videos is how can we compute some statistical queries or train machine learning models without actually revealing any of the sensitive information about the individual instances in our data set. And we'll see that one of those answers is differential privacy. We'll start discussing a simpler approach called Randomized Response, which dates all the way back to 1965 and will help us introduce the main idea in differential privacy, which is randomization. The goal here is to conduct a survey on a potentially incriminating or sensitive set of questions. For example, we could be asking our participants, have you ever committed tax fraud? Have you ever cheated on an exam? Does anyone in your family suffer from some rare disease? And so on. And we would like that our participants answer truthfully with yes or no, even though the question is incriminating or sensitive. The way we're going to motivate the participants to answer truthfully is by introducing some randomization in the procedure, which will give them plausible deniability. Let's look at how this exactly looks like in the case of randomized response. Each of our participants is first going to flip a coin. If the coin lands tails, they will answer truthfully. Otherwise, if the coin lands heads, they will flip a second coin and check. If the second coin lands tails, they will answer yes. Otherwise, they will answer no. So, for example, if I ask you, have you ever cheated on an exam? And you follow this procedure and give me the response yes, I cannot really conclude whether you actually cheated or not. It could be that your first coin landed tails and you answered truthfully, which means you actually cheated. Or it could be that your first coin landed heads and your second coin landed tails, and that's why you answered yes. So your response yes could be either because you really cheated or it could be because of the randomization. So on an individual level, I cannot really tell for sure what is your truthful answer. However, I can still compute the actual fraction of participants that answer yes truthfully. And the way this works is using the following procedure. First, we will compute the maximum likelihood estimate of the responses. So basically, we will look at count number of people that answered yes and divide this by the total number of people. So this will give us the MLE estimate, the maximum likelihood estimate, here denoted with mu hat. But this estimate is not the true fraction of participants that answer yes truthfully. Because we have this randomization step, we get all of these extra yeses. And in order to get the true fraction that answer yes truthfully, we have to correct for the bias introduced by the randomization. And to do this, we compute the following mean, which is 1/4 1 minus mu hat plus 3/4 mu hat. So to see where this comes from, think about the following two probabilities. What is the probability that you respond with yes if the true answer for you is actually yes? Well, it could happen that your first coin lands tails and you directly answer yes, which happens with probability 1/2. Or it could be that your first coin lands heads, which happens with probability 1/2, and then the second coin lands tails, which means you answer yes, which also happens with probability 1/2. Meaning you either answer yes because it's really yes, which happens with probability 1/2, or because you randomly had to answer yes, which happens with probability 1/4. So the total probability for getting a response which is yes, given that you really, the true answer was yes, is 3/4. And similarly, we can compute the probability of observing a yes if the true response was no. Now, using these two numbers, we can correct for the bias in the randomization and compute the actual mean, the actual fraction of participants that responded yes truthfully. And even better, this way of estimating the fraction of participants that answered yes truthfully is an unbiased estimator, meaning that if we have large enough number of samples, we will uncover the true fraction of people that answered yes truthfully. So it's an unbiased estimator, but compared to the standard procedure where everybody directly says yes, no truthfully, we have slightly larger variance. We have 4 times the variance, so you can actually compute this, that it's the correct number, but this is essentially a small price to pay for giving your participants plausible deniability, which means that they are more likely to answer truthfully. And in this case, with randomized response, the main point was that even though I couldn't learn anything about you as an individual, I could learn something about the true fraction. I could learn something about the aggregation of all of the participants. In general, whenever we have some randomness involved, we'll be able to hide minor variations, individual variations, while still being able to compute the general pattern within the data. In the case of randomized response, this was pretty simple. We could kind of compute all of these probabilities in closed form and find the true mean. The question is, how does this work in general? So if we have some complicated query, if we have many features for each of the individuals, if we're trying to kind of give plausible deniability when we're computing like a complex estimate, like the parameters of linear regression and so on. And the way to do this is using the differential privacy framework. And this is what we're going to discuss in the next set of slides. The setup in differential privacy is slightly different. Here, we assume there's a trusted curator which has access to the entire dataset, including all of the sensitive information. In the previous example, this would correspond to a trusted curator which knows all of the truthful answers of all of the survey participants. Now, what the curator wants to do is compute some function on the data and then release the output of that function to the public without revealing sensitive information about the individuals in the dataset. Going back to the example, maybe the curator wants to compute the mean, the fraction of instances which answered yes truthfully, and then release that mean to the public without revealing which instance said yes and which instance said no. And here you might be wondering, well, what is the issue? If we trust the curator of the data, they can just compute the mean and release it to the public. They don't have to say anything about who answered what, and we have privacy preserved. Well, think about the following example. Let's say that all of our participants answered no, right? And we have basically a bunch of zeros. So here we encode the answer no with a 0, and then the curator computes the mean and then releases the mean in the public. Well, by doing so, we've already revealed all of the information in our dataset. Now the public, just by observing the mean, just by observing this 0, can automatically conclude that all of the instances in our datasets must have answered no to the question, right? Moreover, now let's imagine that a new participant comes in, and this participant now answers yes. We see that the new mean, which now the curator computes, and is 1 over n plus 1, and then gets released to the public, is very different from the previous mean. So the public, by comparing the previous mean 0 to the current mean 1 over n plus 1, can figure out that this new instance must have answered yes, because otherwise the mean could not have changed. And in this case, even though we trusted the curator and the curator didn't release any of the sensitive information, just by releasing the output of the function, the public could figure out a lot of information. Now, the way out of this is by adding some randomization, which will prevent us from figuring this out. And in general, what we're trying to do in differential privacy is to say that if I have some function which I compute on a set of instances, I want that the output of that function doesn't change by much if a single instance is included or excluded. Alternatively, we can think about only n vectors and let's say one of those, n inputs, and one of those inputs changes its value. So let's say this particular user changed its answer from 0 to 1, which will of course change the mean. We want that whenever a single instance changes its features or its values, that the output of the function which we're computing doesn't change by much. So both of these versions, whether a single instance has been changed or a single instance has been added or removed, both of them have they're the same under differential privacy treatment, depending on which application we're working on. Okay, so this is what we're building towards. We want to define a method such that, given that only a single instance has been changed or added or removed, the output doesn't change by much. And the way we're going to do this is by constructing a randomized mechanism. And a randomized mechanism is nothing else but computing the function on our data plus adding some specifically constructed noise. And we'll see exactly how this noise is constructed. Now, for some randomized mechanism, we say that it's differentially private if for all possible neighboring inputs, meaning two inputs, two data sets where a single individual is changed, and for all possible outputs, the probability of observing exactly the same output is very close. So, the probability of observing a mean between 0,2 and 0,5 when we have n users divided by the probability of observing a mean between 0,2 and 0,5, where we have n+1 users, should be very close to each other. So we don't want the mean, or whatever function is that we're computing, to change very much when a single instance is changed. And the way we mathematically formalize this is basically we say that we want this relationship to hold for all possible x and x prime. So if we have a data set of n instances for all possible n-1 subsets, we want that for all possible outputs, for all possible subsets of 0,1 to 0,5, 0,2 to 0,7, all possible things that we can get as an output, the probability, the ratio in this case, to be very close to 1. And we quantify this with a parameter epsilon, which tells us how much do we care about essentially distinguishing or not distinguishing between these two cases. So this version is how differential privacy is typically defined. Maybe slightly easier is to read if you apply the logarithm. So if you apply here log on all sides, you get that log of the term in the numerator minus log of the term in the denominator, absolute value should be less than equal than epsilon. So, right, if you apply the log, here the e will disappear, so meaning this term should be between minus epsilon and epsilon, or the absolute value of this term should be less than epsilon. And because here we have the log, we can take the numerator minus the denominator. So the distribution of outputs between x and x prime shouldn't change too much, or the change should be at most epsilon. So the way we should visually think about this, imagine that y is some output that we're computing, and here we have the distribution of this output, of this randomized mechanism, under the first dataset, D1, then the distribution of when one instance is changed, D2, and we want that these two distributions are as close as possible. Or if we go into log space, then the distance between these two distributions should be at most epsilon. And if this holds, then we say that our randomized mechanism is differentially private. Here, just one piece of notation. This symbol captures what is protected. It captures which two x and x prime we consider as neighboring. So it could be that we look at all vectors and we say two vectors are neighboring if one coordinate has changed. Or we can say we look at all datasets and all datasets are neighboring if only one instance has changed. Or maybe only the first 10 features of one instance has changed. So there's some freedom in how you define which two x and x prime are considered neighboring, and this could depend on the application. And remember, where this comes into play is because we say in our definition of differential privacy for all pairs x and x prime which are neighboring to each other. And then how you define neighboring depends on your application. Okay, so then now we know what we want to achieve. We want to achieve that the distribution of x and x prime doesn't differ by much. And the distribution comes from the fact that we're computing some function f, and then we're adding that noise. So adding this noise introduces a distribution over the output space. So how do we achieve a mechanism which is differentially private and satisfies our definition? One of the most commonly used approaches is the so-called Laplace mechanism, where the idea is pretty simple. First, you compute your function on the data, and then you add Laplace noise with variance proportional to the so-called L1 global sensitivity of a function. Let's first think about or talk about what the global sensitivity of a function is in general. Let's say we have some function from some input space x, which takes inputs and outputs d-dimensional vectors. The global sensitivity is defined as the worst case difference between two neighboring inputs x and x prime. So you take your function, compute it on x, you get a d-dimensional vector. You take your function, you compute it on x prime, you get another d-dimensional vector, and then you compute the difference. and then you take the norm of that difference vector. Basically, we want to see what is the worst case, what is the largest possible difference in outputs that we can get for any pairs x and x prime. And then depending on which norm we're using to measure the difference in the output space, we get different global sensitivity. So delta p, where p is 2, will be the delta 2 sensitivity, and if we have p equals to 1, then it's delta 1 sensitivity. So let's look at one example to be a little bit more concrete. Let's say we have an f which takes 0, 1 vectors, so n-dimensional 0, 1 vectors, and outputs a single number between 0 and 1. So this is again similar to our example before, where we have n survey participants, they answer a question with yes or no, and then we output the mean of their answers. So now what we're thinking about is what is the worst case sensitivity of the mean function. So let's say f is the mean. So what we're trying to compute is how large can, for all possible x and x prime, how large can the difference between f of x minus f of x prime, and let's say we measure it into the 1 norm, how large can this quantity get? Where we already computed something like this. In the worst case, all of the inputs are 0, except, so in the worst case, in x, all of the inputs are 0, and in x prime, everything is 0, except one instance has changed from 0 to 1. Then the mean has changed from 0 to 1 over n plus 1. 1 over n. And this is exactly the global sensitivity of the mean. So delta 1 of the mean is 1 over n. So here, just be a little bit careful. So here it's 1 over n, because here we consider that x is neighboring to x prime if one coordinate has changed. If we instead consider that x is neighboring to x prime if one instance has been added or removed, then the global sensitivity would be 1 over n plus 1. So this is the global sensitivity of the mean. Maybe we can give another example. What is the global sensitivity of the median? So what is the median? So the median is the value such that 50% of values are below and 50% of values are above it. So we can have x, which is 0, 0, 0, 0, 1, 1, 1. And in this case, the median is 0. We can have an x prime where we have 0, 0, 0, here a 1, 1, 1, 1, and the median is 1. So the median on data which is binary vectors, the worst case change of the median is from 0 to 1. So the global sensitivity of the median function is 1. So we see that the global sensitivity of the mean goes down as we add more and more data points, so it scales as 1 over n, while the global sensitivity of the median is constant and it's always 1. So of course, here we could reason about this intuitively because the mean and the medians are easy functions, but if f is some complicated function, you actually have to rigorously prove that whatever value you compute is really the worst case value that you're going to get for any possible pairs x and x prime. Okay, now that you know how to compute the global sensitivity of a function, you have everything you need to apply the Laplace mechanism. Basically, you take your data, you compute your function, then you sample noise from a Laplace distribution with 0 mean and variance which is proportional to the sensitivity of the function and inversely proportional to the privacy parameter epsilon. You take the sampled noise, you add it to the output of the function, and you release the noisy version of the output. So here, notice that the variance is proportional to the sensitivity, and this makes sense. If a function is very sensitive, that means that changing a single instance can have a large change in the output, which means we need a bigger variance to cover up this individual change. And similarly, if we want a very good privacy guarantee, meaning we want a small epsilon, so remember, epsilon here measures how close are the two distributions, then again we need a larger variance to cover up the individual differences. So besides the Laplace mechanism, there are many other different mechanisms. One of those is the so-called Gaussian mechanism, where now instead of sampling from Laplace distribution, we sample from a Gaussian distribution where the variance is proportional to the L2 or the delta 2 sensitivity of the function, where now the sensitivity is measured not in terms of one norm, but in terms of two norm of the output vectors. And what Gaussian mechanism allows us to do is not only say that the two distributions are epsilon close to each other, so we have two distributions that are at most epsilon to each other, but it also allows us that we have some additional delta probability in the tails of the distributions. So we allow for some very unlikely events. And this is now called an epsilon delta differentially private mechanism, where the two distributions can be at most epsilon close everywhere, and then there's some small delta where they can differ by a larger amount. But we're not going to go into details about the Gaussian mechanism because it's very similar to the Laplace mechanism. Okay, now going back to the example for Laplace mechanism for the mean function. So as we said before, let's say the function is the mean and the input is binary vectors. Then we computed that the global sensitivity of the mean is 1 over n, which means that in the worst case, changing a single input will change the output, will change the mean by at most 1 over n. So what do? We simply sample from a Laplace noise function where the variance is proportional to 1 over n, and we have the additional epsilon, which is our differential privacy parameter. We sample from this noise distribution, add it to the actual mean that we've computed, and then release the noisy mean to the public. So there's two aspects here. So one aspect is how much privacy are we guaranteeing? So this is captured by this epsilon, right? So how close are the two distributions? And the other aspect is how much, how much is the noisy mean to the true mean? Because whatever we output to the public, we still want it to be useful. We still want that it captures something about our data. And in case of the mean, we can actually quantify that the true mean without any randomization and this randomized mean are very close to each other, and specifically they have an exponential distribution, which means that we're not going to change the output by too much by adding this noise. So it's still going to be useful. In general, computing the L1 sensitivity or the global sensitivity of function is very challenging. Computing the utility, so how good is the randomized output from, how far is the randomized output from the true output, is also very difficult. And the more complicated the function is, the more difficult it is to compute these things. But still, in some applications we can do it, and then we can use the Laplace mechanism. Okay, so how do we do this now for machine learning? This idea or this method of differential privacy is actually very general. So you can imagine that you have a data set of taxi rides, and then you can ask different queries. So how often people take a taxi from New York to Munich or something like that. And then you can answer all of these queries in a differentially private manner without worrying about leaking the information about some particular user. So the function basically you're computing can be anything you can imagine. The question is, how do we train a differentially private machine learning model now? The curator has access to some data set and would like to train a model on this data set and then release the optimal parameters theta star of that model to the public. So you can imagine that we're training a classifier and then we release that classifier to the public, including all of its weights, and we want to do this without releasing or leaking any private information about our users. So as always, we have a data set of n instances, we have some parameters, maybe these are the parameters of a logistic regression model, or a neural network model, or a normal regression model, and so on. And what we want to do is compute the optimal parameters. So usually we're minimizing some loss function where the loss depends on our data set and the parameters, and we want to find the optimal parameters theta star. So if we're doing classification, the loss is maybe a cross entropy loss. If we're doing regression, the loss maybe is the sum of squared errors, and so on. So here, the question is, what do we consider neighboring? And in this case, we can say that two data sets, D and D prime, are neighboring if they differ in only one instance. So the first data set has n instances, the second data set also has n instances, and all of the instances are the same except one instance which has possibly changed its features or its labels. And then we want to have some sort of guarantee that all of the outputs, all of the theta star parameters on D are not that much different from the theta star parameters computed on D prime. Of course, we can even define different notions of neighboring. Maybe an instance has been added or removed. Whatever we define, it's still the case that we want that the output on D and the output on D prime to be as close as possible. So we have different ways to achieve differential privacy. We already talked about one of the ways, and this is perturbing the output of the function. So what we can do is compute the optimal parameters theta star the way we already do, the way we always do. I don't know, solve the normal equations, do gradient descent, whatever you do, compute the optimal parameters, and then add Laplace noise and release the noisy parameters. Of course, to do that, we need to compute the global sensitivity of the entire optimization procedure. And this can be difficult, and in often cases is even impossible to do. A different approach is to perturb the objective itself. So instead of minimizing the standard loss, we can minimize a loss which has an additional noisy term, where this noise is chosen in a particular manner. And of course, we're not going to go into details here, but you can show that minimizing this augmented objective function, which includes this noisy term, will give you outputs which are differentially private. We can also perturb the gradients. So instead of perturbing the loss, we can first compute the gradients for the normal loss, then perturb the gradients and aggregate the perturbed or noisy gradients, and this will also give us differential private output. Yet another way to achieve differentially private machine learning model is to directly perturb the input data set, or to add noise directly to the data. So in this case, basically we say that our function of the data set is the data set itself. We compute the global sensitivity of this function, and then we add Laplace noise proportional to the global sensitivity of the data set itself, essentially. And the way, or the reason why this works is because of the so-called robustness to post-processing property. And this is the fundamental, or one of the fundamental properties of differentially private mechanisms. And basically what this says that if I've already computed my output in a differentially private manner, meaning I've already added noise to it in a differentially private manner, whatever additional computation I do on top of it, whatever post-processing I do, the result will remain differentially private. Or in other words, applying additional function g's on top of the differentially private output m preserves differentially privacy and is also epsilon differentially private. Here there's one catch, that this only holds true if these additional functions that we apply on top of the output don't touch the original data again. And as long as this is true, the output of the post-processing stays differentially private. So the way this works basically over here is we say the function that we're making differentially private is the dataset itself. So we've added noise to the dataset, and now whatever computation we do on top of it, meaning we compute a machine learning model where we compute the optimal parameters, all of these subsequent outputs will stay differentially private. Okay, there's other properties which are very important in differential privacy. One of those is the composition property, meaning now take your data set, apply some first function, make it differentially private, get the first output, then apply a second function, again in a differentially private manner, which you get a second output, and so on. So you can do this k different times. Now you can also say that the entire set of outputs, the first one, second one, until the kth one, is also together differentially private. But now the differential privacy budgets, epsilon I to epsilon k, add up. So the budget of the first one, second one, until the kth differentially private mechanisms, all of them will add up, and you get that the entire composition of these mechanisms is also differentially private with sum of epsilon j differential privacy. Here, most of the time, we talked about differential privacy where we consider only two neighboring inputs, x and x prime, and maybe x and x prime differ in one coordinate, or d and d prime, where two data sets differing in one instance, and so on. The question is, what happens if we have more than one instance or coordinate which is differing? Let's say t different instances are different. Well, then we also get a differentially private mechanism, but now we have a multiplicative factor of t times epsilon. And this, again, follows basically from the previous properties. So in this case, we discussed differential privacy in the Euclidean space, where the input was some arbitrary input space, and the output was d-dimensional vectors, and we computed the global sensitivity based on the LP norm of the difference between outputs. But this actually holds in general, so you can have inputs which are graphs and outputs which are strings, or inputs which are images and outputs which are some other crazy objects, and the fundamental properties and the fundamental way that differential privacy works still holds true. Of course, some of the definitions then change a little bit, but the main idea is still the same, that you compute the sensitivity of the function and you add noise proportional to it. A closely related idea is that of federated learning. So far in differential privacy, we assumed that there's a single central curator which has access to all of the data. But this is not always the case. Think back to the randomized response approach, where each user individually computed the answer on their own, added noise, and then all of these noisy answers got aggregated into a single central place. The idea behind federated learning is something similar. So maybe we're in an application where the users don't trust a central server to properly store or aggregate their data. Maybe we're in an application where the users have location information, location data stored on their smartphones, and they don't trust a central entity to properly take care of all of these location information. Now, if they still want to participate in or help train a certain machine learning model, there's a different approach which we can use, and this approach is called federated learning. So basically what happens is the central server stores the parameters of the model, so these are the parameters of the logistic regression or a neural network or whatever, and then sends these parameters individually to each of the users. The users compute the loss locally on their device. They compute the gradient, they update the parameters, maybe they add some noise to it, and then they send these parameters back to the central server, which then aggregates all of them. And this is the main idea behind federated learning. So the central server doesn't have access to the individual data, but still can learn a model because the individual machines or the individual users send the updated parameters. And this by itself is not going to be differentially private, but if you add special kind of noise, if you add Laplace noise at the source, at the user level, before you send it back to the central server, you are going to get differential privacy. So in summary, often machine learning models contain a lot of sensitive information about the training data. This could be because the models are too powerful, because of memorization, or just because the functions that we're computing are inherently sensitive and they can reveal something about the input or the training data. And a motivated attacker can take advantage of this and reconstruct some of that sensitive information based on the output of the model or the output of the function that we're computing. And in general, doing simple anonymization, such as removing personally identifying information, is not effective, and we need a more powerful approach. Differential privacy is one such approach which can provide mathematical guarantees that not too much information will be revealed about the individuals when we compute a certain function. And differential privacy is very general, so it works for simple functions like computing the mean. It works for complicated machine learning models. It works for databases to which we send queries, and so on. The main idea behind differential privacy was that we add noise to the output of the function, which is proportional to the sensitivity of that function. So if the function is very sensitive to small changes, we need to add a lot of noise. Otherwise, we need to add a small amount of noise. Actually, differentially private computations have been used to compute population queries for the 2020 US Census. And this guarantees that we can get useful information about the demographics of different cities and the population in different parts of the United States without actually revealing any identifying information about those users. Okay, so that was about differential privacy. In the next video, we'll talk about algorithmic fairness.